I'm Mr. Soni and I'm part of AIGuruKul. We are a small research team and we are mentored by my co-author Anupam Pudwar. And I would like to take this opportunity to say that whatever credit you see because of this presentation would go to him and the mistakes are mine. So I will start my presentation and I would like to present on the dynamism in commercial LLM. Is it a boon or pain? Yeah. So this is our conventional RAG pipeline, and as we know that here basically we give LLM a question and we give it some more additional data and we ask it so that it should answer its question based on that data. So basically LLM here acts as an interpreter for the external database. And since we are using a large language model and it is a black box, so the responses generated by LLM are prone to hallucinations. So our research question is like, have you observed LLM give different responses at different times for the same question? And like we observed this case, but this is a RAG pipeline, right? I am giving it a context and I am saying it, you have to answer it based on that context. So how come I am seeing different responses? And what may be the reasons for that? So this is our objective. We want to evaluate what are the causes that affect the variations in RAG. Probably, so our analysis consists of three types of analysis. First, we are trying to see are there any temporal changes in our responses with respect to time. Like, are we seeing any temporal changes? Second, like maybe it's because of the context we are giving to the LLM. The context is controlling the variations, or maybe it's the question itself. That's the third spectrum. That the question may be formulated so that the LLM would take that question and would try to answer it differently. So we evaluated, we analyzed on all three spectrums, and we came up with our conclusion. So how we formed our data set. So this occurred because we formed our data set from images of DLabs ISD, and we use this data set because this is a sample website of a sample website that many of you are familiar with, and it's not a standard data set, but yeah, we use that information to create a data set and do research on that. So we extracted information from iVenture's website. Then we removed all the irrelevant data, like we removed the headers and footers. We converted it to all lowercase and removed all the duplicate information. And then finally, this is the process how vector database, the figure illustrates how vector database is done. So we found our textual informations, and we created a chunks of it. So the creating chunks is a process in that we imply in RAG. We do that because the LLM is constrained by its context window. So this helps us to ensure that we don't go beyond that. And those chunks are then converted into vector embeddings, and hence our whole information about iVenture's website is converted into vector database. So how did we collect that data? So we have our vector database now, and we would ask questions from that vector database or that information of iVenture. And we did that so we made 165 questions, and those are all balanced questions. Like we had, since we wanted to see question characteristics as well, so those questions were made sure that we have some different type of questions there. I will dive into that later. But right now I would want to point out that we recorded responses like at some specific time intervals on the day, and we did that for 3 months. And each answer that was generated was compared to an answer that we thought is a human answer, that a human would expect that. So we had a reference answer, and we kind of evaluated our generated responses to that answers. And we did that using sentence transformers. So basically, sentence transformers, just to say, they just create vectors, and because we have some mathematical, vector space, we can find similarity between them. So sentence transformer is a state of the art here, and that's why we use them. And now we got those similarity scores. So those scores just say that how similar our answer is to the human generated answer. And now our different question types. So this we have the different question types to see the spectrum where we can have changes based on a question itself. So so we have here two sets. First set is like a question can be factual or reasoning based, and second set is a question can be dense or sparse. So what does a question being dense means? That let's say there is a question I ask, and in my database it has a lot of relevant information than that. So I would say that its information is dense there. And if a question has only one or two documents in our entire database, then I would say its information is sparse. Like it's not widely known in our database. So, and I would quickly show you the examples of reasoning and factual-based questions. So, factual-based questions would be straight away based on facts, like who was the guest speaker for a particular session, and based on the particular event, provide some summary and all that. So these type of questions would directly have their answers, their contextual information present in our document. And the reasoning-based questions are more about that the large language model would have to go through, see multiple documents and then concise information. So, for example, describe the role and objectives of iVenture at ISB, and describe the objectives and benefits of iVenture at ISB Women for Innovative Program. So these type of questions are reasoning-based. So now I come back again. Maybe the relevant information, the context that we are giving to the LLM, is it how is it causing how will it cause changes and variability? So simply putting, we have a query here, and we have 5 documents as illustrated in the figure, and by the color they are ranked with most similarity. So document 1 is most similar to our query, and so on document 5 is least similar out here. So what we do is, there is this parameter as top case similarity, and this parameter controls how much context we are giving the LLM for that particular question. So this parameter, this hyperparameter, controls the flow of contextual information. So we varied this hyperparameter and we varied our contextual information, and then we observed our responses there as well. And one particular thing was that, so we started with the default value of 2. Like it would take only two documents, two most similar documents to the question, and we increased it to 5 and 10. But surprisingly, the answers for top K 5 and top K 10 were exactly same, and hence their score were exactly same. There was no change at all. So probably some saturation might have happened there. Yeah, and this is our first glimpse of our results, and these 4 questions are a type of variation that I wanted to illustrate here. Like there, as you can see, that there is no particular trend line here. Like for example, the third question, the bottom left one, there we can see that we have only two values present there, and it's oscillating between those two values, and it's non-periodic in nature. So you don't find a periodic occurrence. Same goes for the bottom right one. There is no trend here. And for the top left one, we can see that majority of time it is answering closer, but there are instances where the score is dropping off. So these are a few questions there where we observe such type of variability. And so what we wanted to do was, we wanted to see, okay, we are observing variability. How much is it? So we plotted a histogram of standard deviations. As we can see, as expected, we see a long tail distribution. Majority of questions didn't vary much, but we can see some questions having increasing standard deviation, and we can definitely see some outliers here. So these outliers just say that something different happened there, and yeah. So now we are getting into how, let's say, I'm changing my contextual information, and how does my mean score change? How does my score change? So surprisingly, I'm increasing the contextual information. I'm increasing the context length. However, for some question did benefit here, like their mean score did increase, but simultaneously for some it decreased. And for some high performing questions, you can see that majority of them are having a score of 1. Like they are they are almost similar to our human answers. And they were consistent here. So even with changes in top K, we didn't see much. And although some outliers are there. But I would like to quantify this. And out of 165 questions, we found 72 to increase, while 47 saw a decrease and 46 saw no change at all. But like this doesn't display a complete picture. So we come to the right diagram. This is just a histogram of change in mean scores. Like I'm just trying to get up how much changes happened at question level. So we are seeing that it's still similar to a normal curve. Here, I still see majority of questions having mean score same as before. We are seeing a difference of maximum population at 0, and it is gradually decreasing at both sides. So, but obviously, some questions saw very little bit of increase, and that's why we are seeing 72 questions as increased, and because of a very slight increase in mean score in the right hand side diagram. Now comes the second part. Like we saw the mean score, but okay, how much variation or variance does it change? So what we did was we plotted the standard deviation with only two similar documents and with top K 10, and then we tried to evaluate how much similar that distribution is. And as visually we can see that they seem to be very similar, and we are seeing some outliers here and there, but the base distribution remains same. So we did a statistical test as well, Vaseline distance. That distance is a statistical measure that just shows how much similar, like how much changes you have to make so that one histogram is similar to other, and it was found to be very low, 0.0013. So suggesting that both histograms are nearly similar. And the same we did with, like, for how much questions the standard deviation they became more concise, or did they lose their convergence. So we found that some questions did benefit here, like they became more precise, they converged here. But the same amount of questions we found, similar amount of questions did lose their convergence because they saw the added information as noise. And some questions still remained unchanged. Like since we were observing no change, and the change in standard deviation, the right hand side figure just tries to display like is there actually a change, but we see that majority of we are seeing a spike at 0. So the variability, the standard deviation didn't change much for majority of them, while it gradually decreased on both sides. So it increased for some while it decreased for some. So yeah, now we wanted to evaluate we wanted to evaluate at question level. Like, are there any relations with a question that is dense or sparse? That would make sense, right? Like, if a question is having more information and I increase the contextual length, then it would capture more information and get a more precise answer. While a sparse question has already captured that information and any added document should be noisy. But surprisingly, what did we see here? That histograms are nearly similar. And the variation in mean score follows the same trend. For some questions that are dense questions, they saw increase while others saw decrease, and some remained unchanged. And same with sparse questions. So this is a striking feature that our basic understanding of RAG pipeline differs with. And now we try to evaluate. Maybe there is a chance that our questions are phrased so that like there may be things related to the question's meaning itself. So we tried to see our distribution for a reasoning-based question or a factual-based question, and we saw that it's still not dependent on that. So the distribution is still a long-scale distribution, and we are seeing here that the same trend is observed. Like for some questions, those are reasoning-based are benefiting, while the other are seeing it as noise, and same is observed for factual questions. So this is so we have seen that observation, and we found out that this basic histogram structure, this distribution repeats itself. So is it more intrinsic than that? Is it based on the data set? This is our future scope of study, and we would we saw that our extensive study doesn't find any conclusive evidences that a particular question type or a particular or the question characteristic affects something. And my results just concluded with average standard deviations, and one good thing that we can conclude from here is, like, if we see the difference between factual and reason-based question, I would like to have your attention there. We can see that the factual average standard deviation is double than the reason side. But factual, they have their answers there, right? Why so? Amazing, right? Striking contradiction in our results. And reason-based, they are supposed to have, the LLM is supposed to look through it and then conclude at some points. But their standard deviation, average standard deviation is less. Also, when we increase the top K, when we increase the context length, we think that, like we saw a not particular trend, but there we are seeing a percentage change. Like majority of them are observing more changes. So our variability on an average is increasing with our increase in context length. And for factual questions, we observed 31% change. So probably we conclude here that those changes may be intrinsic to the data set, and further analysis is needed here. Yeah. So I will conclude my presentation, and I would take you that we are seeing variations, and we didn't find any probable reasoning to it. But we can say that they have their implications as well. For example, the RAG pipeline is supposed to be precise one, but yet these variations can be vague. For let's say CRM, customer management. There, a particular problem type or a bug is supposed to be resolved by only a particular way. And if the model interprets it differently, then it would it would be it would be being there. Similarly, if the interpretation of law documents, there are many cases where we are seeing that the rules are listed out, the rights are listed out in our constitution, but its interpretation is given only to a particular angle. So that angle of visibility or that angle of seeing becomes a very important part here. Same goes for financial strategies. We are going to make our financial strategies based on some indicators and based on some mathematical models. But let's say LLM sees those models and creates financial strategies, but it makes laws. And this last point has been proven by many financial algorithmic traders. And on YouTube, they are giving particular instructions to the LLM, and they are giving the mathematical model. Yet we have to prompt it more and more so that it covers up its mistakes. So initially, it would come up with a strategy that won't make sense. However, this variability and seeing it at different perspectives can be a boon as well. Well, let's say I ask the model to give a particular representation or give a particular answer of what Sri Krishna taught Arjun in Kurukshetra. So at this field, as many of us know that every time you read Gita, you would come up with a different philosophy. So in such cases, the LLM would see different angles and would come up with a creative answer. And for it is also a boon for free text generation tasks like companion chatbots. There, yeah. So that's it, guys. I have concluded my research. Any questions, if needed, you said
it was very interesting. So I'm wondering whether when you take factual questions and you're looking at a human answer to it to compare, is it literally a reproduction of the factual things that are presented in the documents?
Or? Yes.
Okay.
So, the proof to it lies here only that we are observing questions where we are seeing no change at all.
No, I understand that. What I'm asking was, obviously LLM is making predictions, right? I mean, the primary mechanism of producing answer is through predictions, so it's not regurgitating the same thing that it's not reproducing exact words from the document.
Yeah.
And so it's understandable that the difference is more, but I'm wondering whether the substance of the answer or meaning of the answer is the same, even though the words may not be the same.
Yeah, so my answer to your question is that, that's why we use sentence transformers here. So that is a state-of-the-art model, and they have a large corpus of, words, and they have large corpus of English dictionary there.
Okay, so you are using sentence transformers
Exactly.
for the answers, the human answer that.
Exactly. So how am I comparing my generated answer with my human answer? So I am creating a vector space using that state-of-the-art transformer model. And then I'm finding similarity between those two answers in that vector space. And since that is a state-of-the-art model and it has...
So let me ask a related question. Is the difference because, so suppose the actual answer in the corpus is, let's say 100 tokens, okay? And you haven't restricted the LLM answer to 100 tokens, but it's, whatever the default is, 512. So now it is forced to produce 512 tokens as opposed to the real answer which are only 100 tokens, right? So there will be natural difference that will occur, even though, even when you're using sentence transformer and looking at these 100 tokens, when you compare it, because all this extra information is there, it might look different, even though from the syntactic perspective, it's not different.
You are indeed correct, Professor. But what our generated response and the answers, we try to make sure that the context list matches, so that
not just context, but the size of the output matters, right? Because if the size of the output in real corpus is only 100 tokens, but it is, LLM is generating 400 tokens or 500 tokens, whatever your limit is, right? Then it will be naturally different.
There can be changes, but we made sure that such factors are not present. So, like our answers were designed in such a way that, probably.
Thank you. Presenting this slide on extractive text generation, which was jointly done by Tanmay Singh and Bangurwar, and I will be presenting the students. So, the basic problem statement was that when we have a YouTube video, right? So, if you want to extract information out of it, so basically what you will do is you will take the transcript of that video and you will feed that into the LLM, right? But the problem there lies is the video has a noise in it. Like there will be pauses, there will be pauses and all those kind of noises like background noise and all those stuff. So that makes LLM hard to extract relevant information from it, and it will fail to capture contextual understanding. Right. So basically the limitation makes video data unreliable for generating a meaningful summaries and extracting accurate information. This is a basic problem statement here. So we are trying to evaluate the effectiveness of different generation techniques that will help us to compare the performance of multiple LLMs and the approach's impact of the quality and relevance of the information. So basically what we will be doing is we will be trying different techniques like right. So the objective was to create a categorical prompt template to enhance the relevance of the information extracted from the video. And we developed a filtering system to eliminate the noise and video and from the audio-video transcript, establishing accuracy from the text extraction from the contextual calculation. So the methodology study focus on the structure approach to evaluate the impact of different prompt strategies and multi-LLM combinations, utilizing the unlabeled data from the prompt generation. So basically what we will be doing is the video, if we will take the video and if we try to summarize it, it will have the very not very inaccurate responses, the unrelevant responses. So there are basically four methods, the technique that we followed, and the first is the simple prompt. We took that video, we transcribed it, and we fed it to the model to generate the responses based on, and we use a single model here. That will be a small language model that is a Llama 8B. And we noticed that the responses were not that accurate. This was the prompt that were used. In the transcript will be replaced and they are giving some instructions and the title. Right. If the model has the information of related to the transcript, it will be able to produce a good result. But if the model is not capable of, the model don't have that much information about the transcript, it will be giving a rubbish, or it will be start a hallucination, right? So this technique of categorizing it, like the multiple different video has the different categories. From the YouTube, we take the different categories, and for each specific category, we use a different prompt template. Like for example, you have a category of art or music or literature, and for each specific category, we will be having a different prompt template, which will be used to play the inference from there. So we have the labeled data where we have the title of the video, country, category, and that we passed earlier into the simple prompt, and it simple prompt again to the LLM, and it produced some responses that were not that great for some use cases. And now we are trying to do the multi-prompt technique that will be specifying the categories like A, B, C, and we will be even giving it to the one single language model that is the same Llama 8. And this seems that it performs a better focus on a categorical category related content, but still there was not much great responses for some categories like music. And now this is very important, like how do you take the information from music? Because music have a different aspects, like it has tonality, and it has some instrumental noise and all those stuff. And even in music, you have very few words. And sometimes in music, there are not more than 20 length of words. It will be just the pitches and the instrument will be there. And so how you will find the information related to that music? Because the understanding of music is not able to capture that on the transcript, right? But we have the categories, we have the niches, and all those stuff that are fed into the metadata. So that we can utilize in the multi-prompt and specifying them into the multi-LLM, and here the multi-LLM will be very useful. So this is the prompt for the for this multi-prompt. So here we will be specifying the different prompt for different categories. Like for if the transcript length, the transcript is lesser than 20, that particular prompt will be used. And if the category is from art, cinema, literature, and history, and the transcript is not null, this prompt will be specified. And if the category is music, the specific prompt will be used for that category. And fourth one is if all the categories, including MPO and input, then the default will be this prompt. And that technique also did better than a single prompt, but was not in good state. So we try to adapt this multi-prompt and multi-LLM. That basically will try to adapt and switch LLM based upon the categories. And for music, the specific case here is like music, the model have the transcript have very low textual data there. So that will be fed to the online version of the Llama 3 which has the ability to search through web based on the on the metadata that we have, like title, categories, and all those stuff, the limited stuff, and it will be able to search on the web and take the results from there. But again, we can't do this for all the categories because it will be a cost. It may rise the cost for the inferences if we start doing this for all of the conversations. So we have to specify that for the specific categories we need to use the multi-LLM. So if the length of the transcript is 20, we will be using the online version of it because there are the minimum number of textual data there. So it will be feeding that textual data to the web and take the results from there. Okay. And the second prompt is the category, and if the category lies from these, it will be using llama 8b because most of these categories, llama 8b will be having the sufficient knowledge to take the information from there. So we don't need to call the online version or to search on the web that may increase the cost. For the categories like music and which don't have any much transcript, the transcript is like very less. So we can use the online models here. And yeah, and third is the default. So for the prompt development, each category video was analyzed to identify the structure and distinct elements enabling the target approach for extraction. Prompt was tailored to highlight key aspects specific to each category, such as focusing on music style and detailing the music category. And the results were reviewed by 40 human evaluators with deep knowledge on relevant category, ensuring thorough analysis. To maintain objectivity, evaluators provided feedback on generated summaries from three generation techniques that we just saw: single, prompt, multi-prompt, and multi-prompt, multi-analysis, without knowing the source behind it. So these are the results reveal that a multi-prompt and multi-element approach significantly improves response quality because for those questions where we have the model have the very few textual data, it will be able to produce better output. This is generation technique 1, the simple prompt and llama 80 number of LLMs. Here you use your one. For the second generation technique, the prompt was the multiple prompts were used for multiple different categories for one specific model. Right, the number of prompts were 4, and specifically for multi-prompt and multi-LLM, the models were 2 that will switch depending on the use case. And prompt was 4. The conclusion is the multi-prompt and multi-LLM consistently achieve the highest accuracy for across all the categories, especially people, literature, and activities. Like the people travel, travel interest, food interest, and all those questions related to them. And the simple prompt struggle in the categorical text extraction because the simple prompt has will be giving the responses based upon the specific template. That will be same for all the categories, and it has ability to take the response from one large language model that is specifically the AIGuruKul model that have very limited knowledge. The multi-prompt performs better than simple prompt, but it is significantly outperformed by multi-prompt and multi-LLM. Yeah. Thank you. That's it for this presentation. Any questions are welcome. Can you talk about what we are trying to do from this perspective? Yeah.
I will ask a question. So the results that you're seeing, and there was a could it be because the elements are not yet matured enough that hence you're seeing all those differences, but once it gets matured, it will good across the categories. What would be the response?
Yeah, but again, if the model will get mature, the size of the model will increase again. And therefore the cost of operating on those models will also increase. Like the GPT-4 will definitely give a much better responses. But we are not using GPT-4 because it is a proprietary model and we have to pay for it. Whereas this open source model like 8B are open source and we can modify these models and fine tune this according to our use case. And that makes it very useful to do these all experimentations because By doing this, we basically try to make model generate responses as we want on the smaller sizes. Like the 8B is very small that you can even run on the good low GPU settings.
And then one comment and
Yeah.
question. Could there be theoretical reason for the prompt answers to be different or performance to be different across different categories? It is just by coincidence or something about it.
Different response for different categories, right? Yeah. So in a single prompt, the response for all the categories, it will try to adapt and try to respond in a similar fashion. But it should not be the case because the responses for literature will be different from the responses from history. Because from history we will be specifying some dates and all those stuff. But on the literature we will be specifying an idea behind the author or the perspective behind the author. So we need to specify those in the multiple different prompts. Like for history, this should be the prompt and you should focus on the dates and all this stuff. And for the literature, you should be focusing on the idea behind the whole conversation. So that's why the multiple prompt is required.
Clarification question on the multi prompt and multi the way you pick prompt and combine it, is that heuristics driven or is that also something that can be learned or you learn it?
Yeah. So basically, at the initial stage, we try to do trial and error. But as we see there are specific results on some specific candidate, if we are specifying a statement there and we are seeing the noticeable change. So we try to see and reproduce over different prompts and try to take that specific string that we think produce this specific result. That make us sure that this is a string that is responsible for this kind of responses.
So you use your own intuition to match these. But do you think, right? So, but do you think is there a way where you can that process itself can be learned because we as a human can learn that can also be learned by models.
Yeah.
And I bring this especially because at this point of time to create an image using this DALI, which is a ChatGPT prompt, you can write a prompt. You write a prompt. However, that's not a prompt that is used to generate data. The ChatGPT creates its own prompt based on your prompt and your understanding of you, and then writes a new prompt and then uses that.
Right.
So similarly, what I'm saying here is that you might have some prompt, but that's not necessarily the best prompt for whatever answer you want to have. And that process of finding what's the right prompt could itself be learned because we know that other models are doing this. And in that sense, we don't have to do the math that we are really thinking at this point in time because that itself could be learned.
Right. Like that very specifically we call it like a system prompt that is added to your user prompt and respect to the LLM. Right. So in the system prompt, actually these are all the system prompts that will be specified to the model. So user can say anything.